remember, talked about the back and forth between the data generating process and the data itself. And they mentioned the idea of rolling a die and having it come up as, of course, a fair die. In the long term, having equal numbers of ones, twos, threes, all the way to sixes, and a crude drawing for sure, but that's fine. That's what I do on my whiteboard when I use it. But anyway, we do have the view here that we could do, and I notice I'm not in the student view. I'll get back to that later, but for now, we do not expect that the sample of only 12 die rolls will look exactly the same as the population distribution above. This is the long-term population distribution. The die is considered to be exactly fair, so in the long run, it would be the same number, 1/6, or about 17% of the time landing on each of those individual data rolls. So a lot of people guessed correctly. Now, the distribution of 12 die rolls may be completely different than this. It's going to be something that is quite subject to random change. So we'll talk a little bit about that. And yeah, 12 might be exactly 2 apiece, but it's very likely not going to be that way. When you toss 100 coins, I remember reading that or showing that to get exactly 50 heads and 50 tails on tossing 100 coins or a coin 100 times, it's only about 8% likely. Even though 50% is the most likely one, it's not as likely as you would think. So to get exactly 2 apiece, that would be a bit hard to do. Not impossible. It's the most likely event, but it has to share with lots of other events, ranging from, say, 12 landing in the first spot, 12 landing in the second spot, although that might indicate an unfair die. But stuff that isn't exactly even is much more likely to occur. We're going to take a look at a little bit of that coming up. So anyway, they rarely see a small sample that mirrors the population distribution. Small samples are very unlikely to show up as being exact. So large sample size is much, much better. You do expect some fluctuation. So we can do a simulation to see what it could do. And here we have this variable called model.pop. It's a model in the sense that each of the numbers 1 to 6 appears only once, just like an actual die. So they've used the vector notation. They could have used the shortcut. They didn't. We'll save the model.pop in the data frame called dice rolls. So we make a data frame for model.pop and put it into dice rolls. So that's kind of what we're going to do here. Okay, so let's see. We have those that go through 1 through 6. Anyway, the request here is to create a density histogram, the one with the proportions that could easily be turned into percentages if you wanted. Only 6 bins. We don't need the 30 bins. The 30 is not going to help us here. There's only 6 possible outcomes, 6 possible numbers, and colors are completely up to you. So they've got this is the same command as model.pop. They've just used a briefer notation here. So instead of the C notation, which is tedious, they just put 1:6. And it puts the model pop into a data frame called dice rolls. And so they're just doing what they just said they would do. And the hint, get to the hint, remember to use GFD histogram. And by the way, the request is write code to create a relatively frequency histogram. So that's the density histogram, same thing. Let's close this up and start to create that kind of command. And as we did before, we're going to type in GF _ D histogram for density or relative frequency histogram. We can spell that correctly today. Okay, so we're going to go ahead and get it from the model. That is, we're looking for the variable called model, so that gets the tilde in the left corner. And we'll type in model for the name of the model.pop for that, and then we'll have data equals dice rolls. Okay, and then we'll continue. If I can spell dice correctly, was it with an E, of course? Has to be exact. And then bins will equal 6. That's actually an easy command. Just say bins equals 6. Otherwise, it assumes 30. And that seems to be all we need. So we put the bins in. Let's go ahead and run that. See what we come up with. Well, how about that? Uh-oh, I don't know where it went. Oh, boy. Okay, let's go back to where we were. Somehow I lost it. I don't know where it went, but let's see about getting it back. If it'll let me get it back and not erase it. Okay, well, anyway, you saw that it worked out to be like this. So I've got it to run already, but anyway, that's what I got very briefly. And here it is. That's the theoretical distribution, 1 through 6. They didn't put all the numbers down. They should have, 1, 3, 5, and all that. But this works out to be 16 2/3%, almost 17%. And so that's what would happen in the population. But now we shouldn't be surprised at the shape of this. It's a perfect uniform distribution for which each of the numbers has an equal probability of occurring. That's it. So just 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, and 1, 1, of course. And it'd also be a model of what the population looks like in the long run. But what we'd like to do, though, the important thing here is to simulate rolling a die just once by taking a single sample from the numbers 1 to 6 from our model population. So we can use our command sample, and what we'll do is we'll take the item we're looking for, item model.pop, and put down 1, and then it'll roll the die for us. And this time we got a 2. It could be anywhere between a 1 and a 6. You get one roll. That's what the 1 says. So it could be any of those 6 numbers. So what they've done here is they use the do command and let it happen 12 times, 12 separate rolls of the die. Now you see, somewhat randomly, numbers between 1 and 6. And, they didn't do a distribution, but they did list what happened. And there's another way to do it. If you'd rather put it in one particular row, you could do that, and that would be model.pop, 12 on resample. This one appeals to me a little bit more. It's just a little bit more organized. So basically, they have this set up to go. They have a side comment here. Could we just type a 12 into sample model population 12? But it really doesn't do the same thing. They've got it happening right here. In fact, the hint, I think, just says leave it alone. Just hit submit or hit run if you'd rather take a look at it first. Got to X this out. So we'll run it. And it says, error, cannot take a sample larger than the population. Well, they did this on purpose to us. They did say if you try it with the sample command, which is why I don't like to use it, we get an error message, and they did set us up. That command, sample, will take a sample, then remove the number that is sampled. It samples again from remaining numbers, and it's called sampling without replacement. Okay, well, that's the thing. We told it to sample R 12 times, but there's only 6 numbers on the die. And each time you're taking them off the die, this is just not appropriate here. Maybe with a deck of cards, it would be appropriate. But we don't want without replacement. It isn't like we shave off a part of the die. As we roll a 1, we just shave it off. No, that's not happening. And then you look at 6 tries, not 12. So that's where the error is. So you run out of numbers to sample. So without replacement is only appropriate for things that are appropriate that way, like a deck of cards. You take the cards out, it doesn't go back in immediately. But what we'll be doing mostly, I believe, is resampling. That samples with replacement. So if you roll a 1, it stays on the die. Imagine that, the 1 stays on the die. And it replaces it, you can sample it again. So resample is a better situation, at least for us right now. So if you needed without replacement, like a deck of cards, that would only go until you run out of numbers to sample. If they had a way of measuring the cards, the 52 cards, then you would only have 52 to choose from, and each one would be taken out. Say the ace of hearts is taken out, can't get it again. But the die is something else. The coin is something else, and other examples could be used. So that's the gist of the rest of 3.4. Now 3.5 has some more examples. It's just really part 2 of the same idea, except it has more examples for us to look at. A few are examples that we'll try to go through. Let me see if I can switch this up to, I don't think it really matters. It just has a few little quizzes. So yeah, I'm not going to worry about the student view this time, but as of this recording, which is Saturday morning, not many have looked at it yet, but that's not surprising. This is being towards the end of the coverage, so we're not too surprised. Anyway, we take a simulated sample of 12 die rolls, and with replacement for the 6 possible outcomes and save it in a vector called sample1. What code would you use to accomplish this? Looks like a lot of people have gotten it right, and there it is, resample model.pop, 12. The resample would be what you want because it makes sure that you have all those die rolls available. And then we save it as a vector. into a data frame called dice rolls. Okay, fine. And that creates a data frame called dice rolls with a single variable called sample one. And it may seem like overkill to make a data frame for just one variable, but there are things we can do with a data frame, such as making graphs, and you can't do it with just a vector, so it's good to do that. And GF underscore histogram always expects a bar, minus sign, or a little dash, a dash, and then a variable, such that data equals will follow the name of the data frame. And so we can continue with this and add some code to create a density histogram, which is also called a relative frequency histogram, and set bins equal to 6. And it looks like they've got this pretty much going for us. They got most of it. We're going to need to get that GF underscore D histogram going. And the hint will probably tell us that. And this is a relative frequency histogram. So it did give us the first 3 lines, but let me see if I can get in the rest of it. GF underscore D histogram. And then we'll go into tilde, sample one, with a variable, data equals dice rolls, and bins equals 6. So that looks somewhat familiar based on last time. Dice rolls, and then bins equals 6. And spaces are for your convenience. That's all that matters, but you cannot misspell anything. That's the problem. So that seems to be good. We put the bins in. I'm not worried about the coloring. Coloring is fun, but there's so much else to do. That's always my last priority. So we run it. Now we get some sort of activity based on the 12 roles. You can see that each of these, well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that does seem to be correct. And they put it into a percentage based on twelfths, or proportion, I should say. So this being 0.2 is around 20%. And they got something else. It is kind of a random event, so they had also totaled up to 12 rolls. If you look at these as counters, I see the total of 12 would work out. Plus, if you added up all the densities, it should work out to be 1.0, 100%. But they're different. They're different. The ideal case would be to have a perfect uniform distribution, but that just isn't going to happen too often. There's the randomness, the fluctuation that we see. And with such a small sample, you might expect quite a bit of fluctuation. Our histograms will just about always look different. And you could always color it up. They put some colors in. So let's try a larger sample, though. And really, this 12 doesn't look very much like a uniform distribution. Let's try 24, see if it's any better. And essentially, that's the same as before. So I think I'm just going to, okay, we've got it all pretty much right here. So let's look at the hint and just adjust the number of dice rolls, keep everything else the same. So what we'll try to do is change this from 12 to 24. So notice that's all we had to do. It was already in there. And we still want 6 bins for the 6 numbers, so we don't want to change that. And the coloring, you can put whatever color you like. Let's run that. And we got something else. It's not really uniform. The 4 is kind of left out a little bit. That may be only 1 out of 24. 1/24th being about 5%, 4%. So yeah, that looks like about correct there, and all the others are multiples of that. Let's see how it compares with theirs. Theirs was also not very uniform. In fact, probably even worse. They've got a bunch of 2s. And we got a bunch of 3s, although that's only about 25%, 0.25. They got over 30%, 0.3. But neither one is uniform. Is it any better? I don't know. It depends on how you look at it. In theory, the more you put into your sample, the better it'll look, the closer it'll be to uniform. But we're still talking very small sample sizes. That's the problem with this. So we would like to continue with this and simulate more samples of 24 die rolls and call them sample 3, sample 4, sample 5, and plot them out on histograms. Okay, so we can see how that would turn out. Got the model population from 1 to 6. That's the same thing as the C vector notation, C 1, 2, 3, etc. That's just a faster way to do it. So what we want is sample to use the resample command, so we can get those die rolls back in there. And then we'll talk about model pop in 24. Model dot pop, comma, 24. And it turns out we need all of them the same. So model.pop, forgot to pop. So I could just kind of like copy this because I got to do it 3 times in a row. So I'll just save a little time and Command C, and down here Command V, and Command V, at least on my MacBook Pro. So then we have dice rolls. Dice rolls has to have something similar to before. That was data frame, data dot frame, and we'll talk about the 3 types of samples we have in order: sample 3, sample 4, sample 5. So comma, sample 5. Okay, so we got that. So then we also would like to get the histogram going. They've got it started for us. They've got GFD histogram with sample 3. That equals dice rolls, and then they put the colors and the fill in there, the bins, and they've got the parentheses there. We just need to make sure we've got them for all of them. So what I need to do is change this over. So I'll just copy the whole thing and put it down over here. And let's see, Command V. I guess I didn't save it, so let's make sure I Command C on it for me. Maybe not for you, but copy and paste, however you do that. But now notice I'm going to have to change sample 3 to sample 4. I don't want just a duplicate. I want to get a different sample for this. So I go to the next one. I'll just paste it again, but make sure this is a sample 5. So almost all of it's the same. I've just put different labels on them. And I think that's all we're going to need. Actually, no, they wanted the density part of it, so I'm going to have to slip that in at some point. So I'll do that over here. That's going to be connected with the percent key, greater key, the percent key, and then GF underscore density, and then the parentheses. Okay. I may have to look at the solution for this one. This one is starting to get away from me a little bit. So I guess I'll need the sample 3. Let's just see if it runs. I think I may have blown it. Yeah, I didn't do it. Okay, so let's see what happens. You always get the solution, trying to avoid it whenever possible. But let's just see how I made a mistake. Okay, got the beginning part. Got the dice rolls in there. Got the samples defined. Okay, I have to put the percent greater than percent. That's like the chaining command next to the GF density. I did not do that, so I can go back to my script, see what happens. And so for each of these, I need to do that chaining command. So let's go ahead and do that. And let's see if I can just sort of copy this. That might be a simpler way to go. And I'll go back to sample 3, and then I'll just attach it. I guess I could do it on the same line. I don't know if that matters. I think I'll just go ahead and attach it on the same line. And I'll do the same thing here. I'll just have to change it to sample 4. So paste it there. Make sure that's a sample 4. So it lines up with 4. Go back to the bottom one. And let's see. This is going to be, oh, okay. That looks like it's okay, but I need to call that sample 5. Okay, so let's see if we can submit this and see if it'll work. Syntax error, still doesn't like it, so what have I done wrong? I hate to waste your time with all of this, but this may be something you come across yourself. GF density, oh, okay, I do not type the name in. I just leave it empty, and it's supposed to, like ditto marks, just copy what it was from before. So that's something I should have remembered. I tried to make a special point of remembering that. I didn't remember. So I like to have stuff written down. They've emphasized, by the way, while I've got a moment here, to take notes. Please take notes, handwritten notes, however you take notes. You will be allowed to use your notes on the exam coming up. The cheat sheet is also available if you find that helpful. In some ways it is, in some ways it's a bit disappointing in my view, but yet it's better than nothing. And combined with your written notes, that will be what we need. It will be a 75-minute test, and you will not get any extra time after that. So we figure you'll be done well less than 75 minutes. But those that don't follow instructions will simply be cut off at the time limit. But more information on that. But anyway, let's go ahead and submit this. And syntax error still, okay, doesn't like that. So I'm getting a little frustrated by it. Not sure what I did wrong, but let's take a look at the solution. You could just run the solution. Okay, so anyway, what it's done is it's taken another sample. Let's go back to the previous plots and go in order. That's sample 3, and we had another version that didn't really fit the uniform distribution because the sample sizes are too small. It did this little curve fitting thing to it, which doesn't really emphasize the fact that we have uniformity. This one looks like it's skewed. Of course, it's really not. It's uniform. The gray bars should match the green bars exactly in the theoretical world. With a much bigger sample size, it would. Here's another one. And as notice, they have their own random outcomes as well. So I'm not quite sure what I did wrong, but there's something about what I did wrong on my script that doesn't quite match, and I don't want to waste your time looking for that. Something very small, as it so often happens. By the way, on the test, you will not be running R, but we will ask you questions about R. So you should remember what you're doing so you can answer the questions correctly. So that's the important thing. We may be using R in future tests, but not right at the moment. Well, anyway, back to the main point here. These look crazy and do not look uniform. They don't even look similar to each other. There's a randomization, and we don't have enough in the sample size. So do you think they're randomly generated? So you can say no if you'd like, but I'm telling you it is. So if there's something wrong with our simulation, no, just we have too small a sample size. And they were indeed generated by the random process, the simulated die rolls. And at least here, there's no error in the programming. The point to understand is that sample distributions can vary even a lot from the distribution, the population distribution from which they're drawn. And that's called sampling variation, leading to a margin of error in many cases. But small samples will usually not look like the population unless you're really lucky. The very large samples will start to look more and more and more. We'll talk about the law of large numbers coming up very soon. So in this particular area, we have large samples versus small samples. So small samples, as we just said, look really different from the population, but larger samples usually will not. So if we try 1,000, that's starting to become a large number. We'll see more of a uniform distribution. Run the code below to see. So this one, we'll have to go ahead and sample this, get this typed in, create a sample with 1,000 rolls of the die. So that's the resample command, along with the title, model.pop, along with 1,000. No extra commas, please. Add large sample to the dice rolls frame. So we'll simply put this into data frame, data dot frame, that is. And then, of course, we'll type in large sample. Okay, I think that may be it. They've already got it colored for you and everything. Let's go ahead and see what would happen as we run it. Okay, so now, notice they didn't give you counts, they gave you a proportion. And we had said that 16.7% or 0.169, 0.67 rather, to 3 decimal places would be the optimum. And this is looking, although not exactly uniform, much closer to uniform. The advantage of the density is that it avoids the actual counts and just gives you a proportion from which you could easily get a percentage if you needed to. Now, they have something a little different, but theirs is also approximately uniform. If you remember that little graph that we had in blue that showed all the bars being exactly even, 1,000 is still not super large. If you're talking about tens of thousands or hundreds of thousands, that would be more what most people would consider large, but this is still a much better look than before. It's approximately uniform, and it is starting to become what we expected. Wow, a large sample looks a lot more like what we expected it to look like. So that's why they do that. So, excuse me, when you run a process, such as resampling the numbers from 1 to 6, like 10,000 times, you end up with your distribution. We could start to call a population. Now, they've not asked us to do that, but I think I'm just going to take a little side trip and slip another 0 here, just to see what happens. I'm going to run it again. Look at that. It's even closer to a uniform distribution. It's not perfect, but it's pretty close, especially in terms of the density. So, yeah, that's not too surprising. And 10,000 is becoming a large number. And that's what we could call a population. Of course, this would be an infinite population because there's no limit as to how many dice could be rolled or how many time a die could be rolled, that is. So anyway, small samples are unreliable and misleading most of the time, and large samples usually tend to look like the parent population. And for some reason, you saw a distinction that were a lot more sixes than you'd expect. Not only do we have a goodness of fit test for that, which we probably won't have time for, but we would just say this stands out like an unfair die. Throw it away. It is not useful. Okay, we have the simulated population called WPOP. It's looks like a W, kind of, vaguely. I guess it looks kind of like a W. It's I'm sure there's more fancy name for it. I've always thought of the inverted bell curve, the upside down bell curve. This one's got kind of like two different parts to it. So it's just a weird contrived situation. So they call it data weird. They put it in the weird data frame. They color it very colorful color black and all. So we try drawing a relatively small sample from WPOP, and we can save it as small sample and take a look and see whether it looks like the weird W shape. So we have small sample that needs to be replaced by resample for the dice, so we can do it without replacement. With replacement, I'm sorry, and let's put in the W.pop, so that will call up that particular one, and put in 24 dice rolls. Then weird will be renamed as the data frame that came from large sample. I'm sorry, small sample. So yeah, this pronounced it small sample. I think that should be enough because the rest of it has all the commands for the ins and outs of the histogram. And yes, the hint, in case you want to look at it, says use resample to sample without replacement. So yeah, that just kind of says what we just did. So I'm running it, and this doesn't look like a W so much. It just doesn't have nearly enough data. I mean, the 1 and the 3 look okay, but the 2 is kind of like missing. The 4 is too low. The 5 is okay. The 6 is way too low. It looks like there's a lot of things wrong with this. So there's just something amiss about it. They got something else. They got, well, strangely, what they got was almost exactly the same. Well, I guess, no, the 4, they've got a lot more in their 4 column than I do. So sometimes they look almost the same. But this is a random situation, so you shouldn't expect to see the same thing twice. The 24 just is not a large sample size. So if we change this over to 1,000, then we'd have something to talk about. So let's see about doing that. We'll rename large sample as a resample process from the W, capital W dot pop population, and put in 1,000. So that's more of a larger sample. You can write 10,000 if you like. But weird is the data frame that comes from large sample. So it's just sort of a repetitive thing that says we have to use that. And let's run it, see what they got. So this is looking more like the W that we started with. Just to refresh your memory, it was back here. And now with 1,000, not 10,000, but 1,000. These are not the same, but it looks like the W shape is basically intact. How about that? Now what they got, something a little different, a little bit different, but it's very close to what we have here. They're both basically W's. It looks pretty close. So anyway, you have a little quiz you can answer there, and if you'd like. I would definitely go for the large sample size. The small sample size, I hear that sometimes in sports broadcasts. You know, somebody's going 2 for 5 and betting 400, or they shot 2 free throws out of 5. But 5 free throws or 5 at bats in baseball is just not enough to really say much of anything from. And unfortunately, sometimes they do that. They'll make a big deal out of next to nothing. But anyway, that's beside the point. The pattern at large sample sizes, the pattern that large samples tend to look like the populations they come from is called the law of large numbers. Yes, I've been saying that. So the law of large numbers just about guarantees that if you get a sufficiently large size, you will have a number that's extremely close to what's theoretical, assuming, of course, that you have a fair experiment, and a fair die, or a fair coin, or whatever it may be. And if not, then you've got strong evidence that you do not have a fair die or a fair coin. We're not going there. So in case of dice rolls, even in the weird W-shaped population, we know what the true process looks like because we made it up ourselves and we generated random samples. The smaller samples vary so much they're hardly even worth it. very few of them looking exactly like the process or even close for that matter. A very large sample will look more like the population. It's unusual in real research to know what the process looks like. We rarely have an opportunity to collect truly large samples also. That's the problem. There's money, there's time, there's all kinds of issues involved in that. So sometimes you have to get by with smaller samples. In fact, they have a special distribution that used to be primarily used for smaller distribution of samples, although there's a lot of margin of error contained with that. Anyway, we usually have access to small sample distributions, and usually just one. So the realities of sampling variation, which you've now seen, makes our job very challenging. You can't just look at a sample distribution and infer with confidence what the parent population looks like, unless you have the luxury of getting big samples. Of course, R does this for you. You don't have to flip a coin 10,000 times or roll a die 10,000 times. So this is a very good simulation, one of the big advantages of the technology used like this. If you have a good guess as to what the process looks like, you shouldn't be too quick to give up our theory just because the sample doesn't look like it supports it. The die rolls is easy advice to take. Something really unlikely happens in a sample, like 24 rolls in a row come up 5, which is possible, although I'd have to say extremely rare. We'd stick with our theory. We'd say that, yeah, this is just an anomaly, or perhaps you have an unfair die, but we'll just assume fair dice to make it easier. Now, 5 coming up 20 to 24 times in a row is still possible to occur by random chance, but extremely unlikely. I won't give you the odds against that, but that would be really hard. Anyway, when you're dealing with real-life variables, variables for which the true data-generating process is fuzzy and unknown, it's more difficult to know if we should dismiss a sample as mere sampling variation just because the sample is not consistent with our theory. So we get into this gray zone and you're not really sure. So it's important to have a way to look at our sample distribution and ask, how reasonable is it that the data we could have generated really represents our current theory of the process that generates our data? But simulations can be really helpful in this regard. Looking at what a variety of random samples look like, we get a sense as to whether our particular sample looks like a natural variation, or maybe it sticks out as wildly different. And if it is wildly different, you may have to rechange your thinking of how things are going, like maybe the bus schedule has changed, more buses, less buses, et cetera, et cetera. So I hope that helps, and the idea is to get more samples, and anytime you can generate it with a simulation, go for a large number, at least 1,000, I would say. I wouldn't waste my time with 12 or 24, except as a learning tool to say that, oh yeah, this really wasn't that good after all. So we have that on the agenda. So anyway, we're getting ready for the test on the September 30, October 1 timeline. And we'll have more information on that. This is for the Tuesday lecture, by the way, Monday or Tuesday lecture for September 21 and September 22. And we still have another lecture or two to go. Want to get to the end of Chapter 3, have a little bit to say about the Jupyter Notebooks, but that will not be extensively used. In fact, they recommended that I not really put it into play, but since everybody else just about is doing it, that's one thing I have not done. Maybe that's part of the reason we're ahead, because I haven't stopped to look at these Jupyter Notebooks. They never did give me a good reason for having them, but she did suggest I could just skip them. But I'm not going to skip them. We're not going to make a big deal out of them, but they do have some advantages. It looks like they've got some, kind of like the course Kata does, some interactive questions that you can use, and you could even submit, and I'll see if I can put that as part of the 5% or something like that. We're not going to make it a large part of your grade, but it's something we want to give you incentive to do. So more on that next time on the live lecture coming up on September 23 and 24, depending on your section. And we'll have more information about the test coming up. The day before the test, I should just be doing review. Any questions you may have by email or chat or live in person would be good. And I'll answer whatever I can about that. This is my first time through teaching this type of class as well, so it's a challenge for all of us. Okay, that's about all I have for today, and we'll see you live on the 23rd or 24th, and have a nice day.